Okay, so in previous lecture we have completed our first module, that is stepper motor. Now from this particular lecture we are going to start our second module, which is a switch reluctance motor. So as I have already explained in previous class, that is switch reluctance motor is similar to the variable reluctance stepper motor, which is operated under closed loop condition. Okay. So construction is somehow similar to variable reluctance stepper motor, but depending upon the number of tooths in stator and rotor, there are various configurations, and the working is also similar type of or similar to that of a VR stepper motor. Only this particular motor will run in a closed loop condition. Okay, and due to the various features of this particular motor, the operating cost or general cost of this particular motor is less as compared to the VR stepper motor, and therefore in maximum applications now the induction motor drives as well as the series motor drives, DC series motor drives, have been replaced with a switch reluctance motor. So from this particular lecture onwards, we are going to discuss the switch reluctance motor in detail. So today we are going to study the features of this switch reluctance motor, construction and working of switch reluctance motor. So let's start this lecture with a switch reluctance motor, which is nothing but SRM, abbreviated as SRM. So as I have already explained, the switch reluctance motor is similar to the VR stepper motor, which is operated under closed loop position. Okay, now I think all of you are familiar with the closed loop operation of variable reluctance stepper motor. So in closed loop operation of variable reluctance stepper motor, after each pulse, the position of rotor is sensed, and this particular position is given as a feedback to the input sequence controller, that is which generates the required sequence for the operation of uh, variable reluctance stepper motor. And basically the second pulse is given only after the first pulse operation is get completed. Okay, so that is actual closed loop control of a variable reluctance stepper motor. So switch reluctance motor is also similar type of this VR stepper motor, which is operated under a closed loop condition. So definitely, as this particular motor is operated under closed loop condition, so we required certain rotor position feedback systems. Okay, because after each pulse, which is given as excitation to the stator phases, we have to sense the position of rotor. Therefore, we require the rotor position sensor circuits and that entire rotor position feedback systems. Okay. But this particular SRM has several advantages over a variable reluctance stepper motor, and some of the important advantages are: the first one is its operating efficiency is high. Okay. Second one is the SRM generally gives the good performance in terms of torque to inertia ratio. Okay. So this particular motor generally gives the high value of starting torque, and it has a very good performance in terms of torque inertia ratio. Therefore, these DC series motors which are used in certain applications, that DC series motors can be replaced with the SRM. Okay, because the SRM generally produced the high value of torque, and it has a good performance in terms of torque to inertia ratio. Second one is this particular motor. Third advantage is this motor generally has a maximum operating speed. Okay, so the operating speed of this motor is also high, and its construction is simple. Uh, so that construction is simple because there is no any terms of windings or permanent magnets which they are on rotor. So rotor is simply made up of the stack of different lamination which consist only number of tooths on its rotor periphery. So construction is simple. Now, how we discuss this term which is related to efficiency. So why we say this efficiency is high? As rotor does not consist any sort of winding, therefore the copper losses which takes place in rotor is equal to zero. As there is no any winding present on rotor, therefore the magnitude of copper losses which takes place at rotor side is equal to zero. So there are only stator copper losses in case of SRM, and due to reduction in these copper losses in case of switch reluctance motor, the operating efficiency of this motor is high as compared to conventional DC series motor and induction motors. Therefore, due to this higher efficiency and the maximum torque which is generated by this motor, now it is general practice to replace series motor and induction motor drives with SRM drives. Okay. Now, it's generally this motor is available in different sizes. So various sizes motors are available with a different power ratings and speed ranges. And due to this entire things, it has ability to operate in four quadrant operation. So now I think in drives you will study this four quadrant operation of a motor. Okay. So there are total four different quadrants, and each quadrant there will be certain different behavior of a motor operation. So in detail you will study that four quadrant operation of a motor in case of a drive, and this SRM can be able to operate in these all four quadrants of drives application, and due to this this SRM drive is now the attractive solution for the variable speed application. So the applications where we have to vary the speed of a motors in such variable speed application, now SRM will be the attractive option, or it will be the attractive solution over the conventional motors which are used in actual drive system. Okay. So SRM drive is the better alternative to the conventional DC series motor drive and variable speed induction motor drives. Now, why it is better operation, better alternative for DC series motor drive? That is due to the higher value of torque to inertia ratio. Okay, and good performance related to torque inertia control. Second one is why it is better for variable induction motor drive, because of its higher efficiency and maximum operating speed. So it will operates under a wide range of speed variation, and due to this we can use this SRM drive as a better alternative for the DC series motor and variable speed induction motor drives in actual applications. Okay. Now, as I have already explained, SRM always works under closed loop condition. Okay. There is only one mode of control operation for this SRM, which is the sensorless control of SRM, and that is only one way of open loop operation of this switch reluctance motor. Otherwise, for most of the applications, we have to run this SRM under closed loop condition. Therefore, the performance of this SRM drives is entirely depends upon the control system which we use in that drive. Okay, so whatever control strategy which we use, whatever control system which we use in this SRM drive, so over that control system, the entire performance of this SRM drive will depends. Okay. Now, there is a rapid development in various controllers and the semiconductor, that is the power electronic devices and components, and that will made the implementation of semiconductor switching circuits and controllers with a lesser cost. So again, we have to excite the stator phases of this switch reluctance motor with the help of the external DC excitation, and for this purpose we use a one particular semiconductor switch in each phase. Okay, so there is a rapid development in these semiconductor technologies. Now there is a rapid development in these power converter technology, power electronics technologies, and the digital controllers which are used in control system. And due to this particular rapid development, now this implementation of the semiconductor switching circuits and controllers are easy and economical. So therefore, in many of the industries, now SRM drives will be the better solution for the conventional drives, which are the DC series motor drives and variable induction motor drives. Okay, so these SRM drives will now work with a full potentials in many of the industrial applications. Okay, so these are the general features of the switch reluctance motor. And now after these features, now let's move towards the construction of SRM. So as I have already explained, the construction of a switch reluctance motor is similar to variable reluctance stepper motor. Now you are familiar with the construction of a variable reluctance stepper motor. So let's recall that particular construction. So when we discuss variable reluctance stepper motor, then that stepper motor consists again stator and rotor. So when we talk about the stator of this variable reluctance stepper motor, that stator is made up of the different stackings or different laminations. So that is a simple made up of the stackings which are suitably punched using a various silicon laminations uh, at of appropriate dimensions. Okay. So similarly, the SRM motor stator is also made up of the stackings of suitably punched silicon laminations of appropriate length, and that number of silicon laminations are stacked together to construct this stator. Again, at inner periphery of that stator, it consists the different salient poles. So it is general practice to build the stator with even number of salient poles. Okay, so there may be 2 poles, there may be 4 poles, 6 poles, 8 poles, and so on. So such even number of salient poles are present at inner periphery of this SRM. Okay, so if you look towards the constructional cross-sectional area, then that inner periphery of this stator, even number of salient poles present. Now, this SRM consists of concentric windings. So that concentric windings are generally formed in terms of coils, and we place these particular coils on each and every stator pole. So there is coil placed on every stator pole. Okay, so coil is placed on every stator pole. So here also suppose we place a coil. Now, the diametrically opposite pole coils are connected in series. So, say this is second coil, this is one coil, and third, suppose this is third coil, and this is fourth coil. We connect these diametrically opposite coils in series so that there will be formation of a phases. Okay. So, if there is a n number of poles on stator, then the number of phases for that motor is equal to n by 2. And to obtain this n by 2 number of phases, we generally, or it is conventional practice to use even number of stator poles in case of a switch reluctance motor. Okay. So the diametrically opposite coils are generally connected in series to form a stator phases. Okay. So there may be a 2-phase, 3-phase, 4-phase, 5-phase, 6-phase, and so on. Okay. So if stator consists n number of even poles, then the total number of phases for stator is equal to n by 2. Now, while constructing this switch reluctance motor, the overlapping of coil in the different stator poles are avoided, and this overlapping is avoided to minimize the mutual inductance between the phases. Okay, if there is a overlapping between the adjacent stator coils, then definitely there will be certain mutual inductance between that coils, and that mutual inductance will definitely affects on the working of SRM, and to avoid this, generally overlapping is avoided. Okay, so the overlapping are generally avoided, and how we avoid this particular overlapping. So for this purpose, whatever n connections of coils are there, that n connections should be shorter. So whatever these connections of coils are there, that coil connection should be shorter or as short as possible. That will avoid the overlapping of coil, and that will avoids the mutual inductance, or that will minimize the mutual inductance between two phases. Okay, that is the construction of a stator. Now let's come towards a rotor construction. So rotor contains no winding or permanent magnet. So similar to variable reluctance stepper motor, there will be no any winding or no any permanent magnet on rotor. So again, this rotor is made up of the different steel laminations. That number of steel laminations are stacked together to form entire rotor structure. Now, laminated rotor is generally used to minimize the eddy current losses. Now, you are familiar with that. You are studying this concept of eddy current losses from semester 3. So in each and every machine, the rotor and stator structure is generally laminated to minimize the formation of eddy current in that armature, and you can say that stator and rotor structure, and that will reduce the eddy current losses and that will improve the efficiency of that machine. Therefore, in SRM also the stator and rotor structures is a laminated structure. Okay. So all these laminations, steel laminations which are there for rotor, that all laminations are stacked on the shaft and there will be formation of an entire rotor structure. So when we look towards the construction of this rotor for SRM, that rotor is a very simple structure. So it is a mechanically simple structure that simply consists the rotor shaft, the number of rotor laminations which are made up of a steel, and that all laminations are stacked together on that rotor shaft so that there will be formation of entire rotor. So on the outer periphery of that rotor, it consists the number of teeth, which are generally termed as a number of rotor teeth. Okay. So if you look towards this particular rotor, number of rotor teeth are present on the rotor periphery. Now, by selecting this number of phases, which are generally stator phases, the number of stator poles and number of rotor teeth, it is possible to construct this switch reluctance motor in different configurations. Okay. So these various configurations of a switch reluctance motors depends upon how many stator poles are present, how many stator phases are there, and how many rotor teeth are present in the given SRM. So for certain examples, now a few such commonly used configurations are shown in figure 2.1 over here. So if you look towards this first figure consists total 6 rotor poles. Okay, sorry, 6 stator poles, and there are 4 rotor teeth. So this particular configuration is 6 as to 4 configuration. So first number is generally the number of stator poles. Second number in configuration indicates the number of rotor teeth. Okay. Second configuration is 8 by 6 configuration. So in this 8 by 6 configuration, you will find total 8 number of stator teeth and 6 number of rotor tooths. 8 number of stator poles, and 6 rotor teeth. Similarly, the alternate configuration may be 10 by 4 configuration. So where we found a 10 rotor poles and 4 teeth. Alternately, there will be 12 by 8 configuration. So that is the 12 number of rotor teeth, stator poles, and total 8 rotor teeth. So for this particular different configuration, now we can easily determine the value of a step angle. So whatever step angle which we required or which we calculate for SRM, that step angle can be calculated by a similar way in which we have calculated step angle for VR motor, that is variable reluctance stepper motor. Okay, so how we calculate step angle for variable reluctance stepper motor? So that step angle is calculated by theta, represented by theta s, and which is equal to 360 degree divided by m multiplied by nr, where m is the number of stator phases, nr is the number of rotor tooths. So number of stator phases, now m is the number of stator phase, that means how whatever stator poles are there, stator poles sorry, divided by 2, that will give us number of stator phases. So let's take first configuration, 6 by 4 configuration. So for this 6 by 4 configuration, what will be the value of step angle theta s? So the value of step angle theta s for this 6 by 4 configuration is or can be calculated as 360 degree divided by number of stator phases. So there are total 6 stator poles. So 3 number of phases are there. Okay, so that is 3 multiplied by nr. nr is the number of rotor teeth. How many rotor teeth are there? There are total 4 rotor teeth. So 3 phases, 4 rotor teeth. So the denominator term comes to be 3 multiplied by 4, that will be 12, and 360 divided by 12, that comes to be 30 degree. So whenever the configuration of SRM is 6 by 4, then there will be step angle of 30 degree for this 6 by 4 configuration. When we talk about 8 by 6 configuration, so for 8 by 6 configuration, now what will be the step angle? So 8 means the number of stator phases equal to 4, number of rotor tooths is equal to 6. So 4 multiplied by 6, that comes to be 24. Okay, so denominator term is equal to 24, and 360 divided by 24, that comes to be 12.5. I think 360 divided by 24 is 12.5. Yes, so please check 360 divided by 24. So whether that is 12.5 or 15. That is 15 degree. Okay. So 360 upon 24, that comes to be 15 degree. Okay. So for the second configuration, that is for 8 by 6 configuration, the step angle is equal to 15 degree. Let's say third configuration, which is the 10 by 4 configuration. Now for this 10 by 4 configuration, the number of stator phases is equal to 5. Denominator term is equal to 5 multiplied by 4, that becomes 20. 360 divided by 20, that is equal to 18 degree. So for third configuration, which is the 10 by 4 configuration, the theta s is equal to 18 degree. And for fourth configuration, which is 12 by 8 configuration, theta s is equal to number of stator phases equal to 6, 8 6 are 48, and 360 divided by 48, so I think this comes to be 7.5. Okay, 360 divided by 48 is equal to 7.5. So theta
Yes,
is
sir.
7.5 degree. Okay, so whatever step angle which is there for this SRM, that step angle is depends upon the different configurations. That means how many number of stator poles and how many number of rotor teeth are present in SRM configuration. Now, the basic block diagram of any SRM drive is as shown in figure 2.2. So this is the basic block diagram of SRM drive. Now, if you look towards this block diagram, you will find a closed loop system. Okay, so the power converter circuitry is actually the switches which are power switches or semiconductor switches which are present in each stator phase. So this SRM is excited with DC supply. So that means this DC supply is given to this power semiconductor or power converter switches or power converter block. Now this controller generally generates the gate pulse, that is the switching sequence. This switching sequence is given to the gate driver circuit of this power converter circuitry. So there is a in between this power converter and controller, there is a gate driver circuit. Okay. Now the output of this power converter circuit is actually your the logic sequence, which is for excitation of the phases of this particular SRM. So this particular current is sensed by current sensor through signal processing unit. It will given to the controller, and second input to this controller is the position sensor. Okay, that is the position of rotor. So again, that position is sensed with the position sensor through signal processor. It will given to controller. Now, what is necessity of the signal processors blocks in current sensors and in current and position values? So whenever we sense this current and position of that sensor, that particular values are actually analog values, and for controller we require the digital inputs. So it is necessary to convert this analog sense or analog parameters like current and position into the digital parameter. Again, it may be required to filter out certain unwanted signals from this current or output of current sensors and position sensors. It may be required to amplify that particular output. So sensor output, it is need to amplify that output. That means in general, whatever sensor output is there, we have to condition that sensor output before giving that sensor output to the controller. So anyhow, controller requires the inputs from in terms of digital values, and for this purpose we require certain signal conditioning units. So basically that signal conditioning or signal processors are generally the combination of amplifiers along with ADC, or that may be filtered along with ADC and so on. So as per the requirement, as per the value of sensor output, different signal processors can be used, which converts the sensor output into appropriate signal which can be provided as an input to controller. Okay. So depending upon the rotor position and depending upon current which is flowing through a particular phases, the logic sequence is generated by this controller, and that logic sequence is given to gate driver circuit of power converter, and accordingly the particular phase of that SRM is excited. We are talking about stator phase. Okay, so particular stator phase of that SRM is excited and motor will run with a desired step which depends upon the sequence, okay, and the modes of excitation. Okay, so this is the general block diagram of any SRM drive, but this is with sensor drive. Okay, that means the closed loop control. If you look towards this block diagram, entire control is the closed loop control of a closed loop control. Now along with this current and position sensor output, controller may give an input as a required step angle. So whatever step angle which is required, that step angle is given as an input to this controller. Okay, we are going to discuss that particular things in actual control circuits of this SRM. Okay, so this is about the construction of a switch reluctance motor. Okay, now let come back towards working of this switch reluctance motor. How this switch reluctance motor will work. Now, working of a switch reluctance motor is similar to the variable reluctance stepper motor under closed loop condition. So, if we recall the working of a variable reluctance stepper motor in closed loop condition, in that operation, we generally provide the excitation pulse to a particular stator phase only after the completion of an initial pulse. That means when we provide first pulse, after that first pulse, the motor will runs with the desired step angle. We sense the position of rotor, and after rotor comes to stationary or stable condition, or after rotor moves with the desired step angle in forward or backward direction, then and then only the second excitation pulse is initiated by the controller, and that will provided to the next stator phase. Okay, so unless and until the working of a motor for a first pulse have been completed, there will be no any provision of a second pulse. So in simple, the working of a variable reluctance stepper motor, or see in simple, working of a closed loop control of variable reluctance stepper motor is similar to the single phase excitation mode of motor. Okay, same kind of working is there for a switch reluctance motor. So to explain the working of a switch reluctance motor, we consider the 8 by 6 configuration of this motor. 8 by 6 configuration. Now what is meaning of 8 by 6 configuration? 8 by 6 configuration is nothing but the total number of stator poles equal to 8. There will be 4 stator phases. Total number of rotor teeth is equal to 6. So number of stator phases 4, number of teeth 6. So the step angle is equal to 15 degree. Okay. Now here total 8 stator poles are there. Now 8 stator poles that consist the concentric coil. We connect diametrically opposite coils in series so that there will be formation of 4 phases. We represent these 4 phase coils with a AA dash, BB dash, CC dash and DD dash respectively. So these AA dash, BB dash, CC dash and DD dash, these are the 4 phases of the stator for SRM, which is in under 8 by 6 configuration. Now We energize these four phases with the DC supply through semiconductor switches, which are shown in the switching circuit of this SRM. So that four semiconductor switches are present. One semiconductor switch is there for each phase. So these semiconductor switches are generally either MOSFETs or IGBTs, and the gate driver circuit of that MOSFET and IGBT is connected to the output side of the controller, or that gate driver circuit or gate terminal of this MOSFET or IGBT is excited with the gate driver circuit. So whatever response of gate driver circuit is there, accordingly that gate terminal will open or close. Now let us initially consider the stator phase A and A dash is under excitation. That means we close this switch S1 and we excite stator phase A and A dash. So as this stator phase A and A dash is under excitation, therefore, let's say the rotor teeth 1 and 4 that are aligned along with this A and A dash, and we consider this particular position of a rotor as a equilibrium position of rotor with a angle of 0 degree. So initially we excite this A and A dash, and whatever position of rotor is there, that position is shown in figure 2.4. So in due to this particular excitation of phase A, 1 and 4 phases, that two phases, rotor teeth are under alignment of A and A dash. There is a magnetic locking between stator pole A dash with a rotor teeth 1 and 4, and that we consider as a equilibrium position of this SRM. That means a 0 degree position of SRM. Now next to this equilibrium position, now phase A and A dash is de-energized by opening S1. So we have to open this S1, by that will de-energize the A and A dash, and at the same time we have to excite B and B dash by closing S2. So close this S2 so that B and B dash get excited. Okay. So once B and B dash get excited, so now this is the equilibrium position of a rotor when phase A is excited. Now when we excite B and B dash, under this particular case, the rotor will try to move in counterclockwise direction by a 15 degree, so that rotor teeth 2 and 5 that are came under alignment of stator pole B and B dash. So this will only happen when rotor moves with counterclockwise direction by 15 degree. That means that will be the first step operation. Okay. So whenever we excite phase B and B dash, then now rotor position is 15 degree in counterclockwise direction, and this is happened due to the alignment of this 2 and 5 rotor teeth with a B and B dash stator pole. Okay, so now someone may ask why this particular rotor now not moves in clockwise direction. So in variable reluctance stepper motor, I have already told rotor always try to move in a minimum reluctance path. Okay, so for this particular 3 and 6, if you look towards this next rotor teeth 3 and 6, the air gap is more. That will offers the large value of reluctance as compared to the 2 and 5 for B dash excitation. Therefore, rotor moves in counterclockwise direction by 15 degree. And this particular position of rotor is now shown in figure 2.5 with a phase B excited. Now again, we have to move this rotor by 15 degree in CCW direction, that is in counterclockwise direction. Excite phase CC dash by closing S3 by opening S2. So when we open S2, B dash get demagnetized. Now close this S3 so that CC dash get magnetized. Rotor will again move in 15 degree in CCW direction, that is in counterclockwise direction, and tries to align its rotor teeth 3 and 6 with CC dash as shown in figure 2.6. Similarly, now excite DD dash by closing S4 and opening S3. Once we open S3, CC dash get de-energized. As we close S4, DD dash get energized. rotor will again move by 15 degree in counterclockwise direction, and the rotor poles 1 and 4, sorry, rotor teeths 1 and 4 get in align with stator pole D and D dash. So in this way, by following switching sequence S1, S2, S3, S4, we run this motor in counterclockwise direction. If we have to move this motor by in clockwise direction, we have to reverse this switching sequence. That means for clockwise direction motion, now switching sequence will be S1, S4, S3, S2, S1. So in this particular way, we can change the direction of rotation from counterclockwise to clockwise. But in any direction of rotation, after energizing each phase, rotor will move by 15 degree only, that is with a full step angle. Okay. So this operation of SRM generally depends upon the variation of phase inductances. Okay, and these phase inductances of a stator phase basically depends upon the relative position of rotor teeth with the stator pole, because the inductance is generally depends upon the position, relative position between stator and rotor teeth and rotor teeth and stator poles. So phase inductance may be increased, remains constant, decrease, remains constant, and rises cylindrically. Okay, sorry, cyclically. So in every operation, switching operation, there is a rise in inductance, constant inductance, there may be fall in inductance, or maybe again constant inductance, and this is entirely a cyclic manner. So this variation generally depends upon the overlapping of rotor teeth with the stator poles of a concerned phase. So whatever overlapping is there, this is actually overlapping. So basically inductance which is offered by this particular motor, it generally depends upon this overlapping, how that rotor teeth get overlapped with the stator phase. Okay, so the current in the phase should be forced in a winding when rotor teeth is just entering the stator phases, or when the rotor teeth just entering the stator poles of that particular phases. Okay, so it is therefore to know the rotor position for switching as well as the current flowing through stator winding. So there is a requirement of current flowing through stator winding as well as the actual rotor position. Therefore, in closed loop control of the SRM drive, that means in this block diagram, we have taken both feedbacks. One feedback is from stator current, which is taken by current sensors, and second feedback is actually the actual rotor position. Okay, therefore it is required to take current, stator current, as well as the actual rotor position for the control of this SRM or for operation of this SRM under closed loop manner. So the condition for successful operation of SRM can be summarized with these 4 points. The first one is the number of rotor teeth and stator poles must be even and not equal. Okay, so the how many number of stator teeth are there? Rotor teeth are even, stator poles are also even, but both are unequal. Both should be unequal. And it is general practice to keep the number of stator pole higher as compared to rotor teeth. Okay. Second thing is the stator phase is energized when inductance of that phase is low or increasing. So the stator phase is energized whenever inductance is low. Okay, so whenever inductance is low and or that inductance may be increasing, under that case only we have to excite the stator phase. Third summary point is sensors for rotor positions is required, because along with the stator current we require the rotor position, and the rotor position sensing is an essential for the switching operation at a correct instances. We required both stator current as well as the position of rotor. So along with stator current, we have to use a certain rotor position sensing circuitry, and that rotor position sensing is an essential task for the switching operation at current instances. And fourth summary point is the flux density is changing in magnitude and the direction in the magnetic circuit when rotor moves. This is actual common practice for any magnetic circuit. Whenever there will be change in the rotor, there will be change in flux density. Okay, the magnitude of that flux density also changes, as well as the direction in the magnetic circuit is also changes, and that will affects or that will creates the iron losses in this circuit. Okay, so how to minimize these iron losses? So to minimize these iron losses, we generally use a laminated rotor and a stator structure. Okay, so when we recall, if we recall hysteresis losses and eddy current losses, that hysteresis and eddy current losses are generally termed as a constant losses, or that are also known as a iron losses. And these losses are only happen or only produced in the magnetic circuit due to the variation in the flux density whenever there is a movement of rotor. If rotor is held stationary under stationary condition, generally the rotor eddy current losses and hysteresis losses are negligible. Okay, so rotor hysteresis and eddy current losses are negligible whenever rotor is held stationary. Okay, so these losses, which are iron losses, that depends upon only the or that losses are created due to the variation or change in flux density and the direction of magnetic circuit whenever there is a movement of rotor. And to reduce these iron losses, it is convention practice to manufacture or to construct stator and rotor of SRM with a lamination. That means the stator and rotor both are laminated structures. Okay.